Bismillahirrahmanirrahim. Assalamu alaikum. We will start our lecture 4 of Plasma Physics 2. Course code is PHYS4131. We start our fourth lecture with topic electromagnetic waves parallel to B naught. To study electromagnetic waves parallel to B naught, we let K lie along the z-axis and allow E1 to have both transverse components Ex and Ey. Then we have K is equal to Kz hat, E1 is equal to Ex x hat plus Ey y hat. The wave equation for the extraordinary wave can be used, but we have to change K from Kx hat to Kz hat. Then we write the components for Ex and Ey as omega square minus E square K square into Ex is equal to omega P square over 1 minus omega C square over omega square into Ex minus iota omega C over omega Ey. Similarly, we write the component Ey omega square minus E square K square into Ey is equal to omega P square over 1 minus omega C square over omega square into Ey plus iota omega C over omega Ex. We now use the abbreviation alpha, which is equivalent to omega P square over 1 minus omega C square over omega square. Then we put this abbreviation in the above equations. Then the equation for Ex and Ey can be written as omega square minus E square K square minus alpha into Ex plus iota alpha omega C over omega Ey is equal to 0. Similarly, we have omega square minus E square K square minus alpha into Ey minus iota alpha omega C over omega Ex is equal to 0. We now set the determinant of the coefficient to 0. We have omega square minus C square K square minus alpha to power 2 is equal to alpha omega C over omega whole square. Further simplifying this, we get omega square minus E square K square minus alpha equal to plus minus alpha omega C over omega. Thus we get our final results. Omega square minus E square K square is equal to alpha into 1 plus minus omega C over omega. We can rewrite this expression, and rearranging we get omega P square over 1 minus plus omega C over omega. The minus plus sign indicates that there are two possible solutions corresponding to two different waves that can propagate along B naught. The dispersion relations are given by n square is equal to C square K square over omega square, which is equal to 1 minus omega P square over omega square over 1 minus omega C over omega. We call this R wave. Similarly, we have n square is equal to C square K square over omega square, which is equal to 1 minus omega P square over omega square divided by 1 plus omega C over omega. We call it L wave. The R and L wave turn out to be circularly polarized. The designations R and L meaning respectively right hand circular polarization and left hand circular polarization. The geometry is shown in diagram. The geometry of right and left-handed circularly polarized wave propagating along B naught can be viewed in the diagram. The electric field vector for the R wave rotates clockwise in time as viewed along the direction of B naught, and vice versa for the L wave. Since these two equations depend only on the value of k square, the direction of rotation of the electric field vector is independent of the sign of k. We observed that the polarization is the same for the waves propagating in the opposite direction. Let's summarize this. The principal electromagnetic waves propagating along B naught are a right hand and left hand circularly polarized waves. The principal waves propagating across B naught are a plane polarized wave. We also called them O wave, and an elliptically polarized wave X wave. That's the end of our first chapter, waves in plasma. This is the fourth chapter of book of F. Chen. Our next chapter of plasma physics 2 is diffusion and resistivity. Book chapter 5 of Francis F. Chen is closely followed for chapter 2, diffusion and resistivity. Our first topic of chapter 2 is diffusion and mobility in weakly ionized gases. जितने भी वीकली आयोनाइज्ड गैसेस हैं हम उनके लिए डिफ्यूजन एंड मोबिलिटी को स्टडी करेंगे. Any realistic plasma will have a density gradient. जितने भी रियलिस्टिक प्लाज्मा होंगे वहाँ पे डेंसिटी ग्रेडियंट होगा और प्लाज्मा जो है वो डिफ्यूज़ होगा टवर्ड रीजन्स ऑफ लो डेंसिटी. हमें पता है कि डिफ्यूजन जो है वो मूवमेंट ऑफ ए सब्सटेंस है फ्रॉम एन एरिया ऑफ हाई कंसंट्रेशन टू एन एरिया ऑफ लो कंसंट्रेशन. डिफ्यूजन हमें पता है मोस्टली लिक्विड्स और गैसेस में होती है क्योंकि पार्टिकल रैंडमली मूव करते हैं प्लेस टू प्लेस. The central problem in controlled thermonuclear reaction is to slow down the rate of diffusion by using magnetic field. कंट्रोल थर्मोन्यूक्लियर रिएक्शन करवाने के लिए हमें मैग्नेटिक फील्ड को यूज़ करना पड़ता है ताकि रेट ऑफ डिफ्यूजन को स्लो किया जा सके. It is called a weakly ionized gas when the collisions with neutral atoms are dominant. डायग्राम में डिफ्यूजन ऑफ गैस एटम्स को दिखाया गया है जो कि रैंडम कोलिजन्स की वजह से अकर कर रही होती है. ये बिल्कुल इसी तरह है जैसे हमारे पास ब्राउनियन मोशन होती है. As the plasma spreads out as a result of pressure gradient and electric field forces, the individual particles undergo a random walk, colliding frequently with the neutral atoms. Further, we study the collision parameters. हमें पता है कि जब इलेक्ट्रॉन फॉर एग्ज़ाम्पल कोलाइड करता है न्यूट्रल एटम के साथ तो वो अपना फ्रैक्शन ऑफ इनिशियल मोमेंटम लॉस करता है डिपेंडिंग ऑन द एंगल एट विच इट रिबाउंड्स. इन अ हेड ऑन collision with a heavy atom, the electron can lose twice its initial momentum since its velocity reverses sign after the collision. The probability of momentum loss can be expressed in terms of the equivalent cross section represented by a symbol sigma that the atoms would have if they were perfect absorbers of momentum. Illustration of the definition of cross section is shown here. Electrons are incident upon a slab of area capital A and thickness dx containing n neutral atoms per meter cube. The atoms are imagined to be opaque spheres of cross-sectional area sigma, that is, every time an electron comes within the area blocked by the atom, electron loses all of its momentum. The number of atoms in the slab is given by NN ADX. The fraction of the slab blocked by atoms is given by NN ADX sigma divided by capital A, which is equal to NN sigma dx. If we represent the flux of the electrons by gamma is incident on the slab, then the flux emerging on the other side will be gamma is equal to gamma into 1 minus NN sigma dx. The change of flux with distance is d gamma over dx is equal to minus NN sigma gamma, or gamma is equal to gamma naught exponential to power minus NN sigma x, which can be written as gamma naught e to power minus x over a lambda m. In a distance lambda m, the flux would be decreased to 1 over e of its initial value. फ्लक्स हमारे पास डिक्रीज़ करेगा 1 ओवर ई टाइम्स ऑफ इट्स इनिशियल वैल्यू. यहाँ से हम वैल्यू फाइंड कर सकते हैं मीन फ्री पाथ की. द क्वांटिटी लैम्डा एम इज़ द मीन फ्री पाथ फॉर collisions, which can be written as lambda m is equal to 1 over NN sigma. After traveling a distance lambda m, a particle will have had a good probability of making a collision. Then we have the mean time between collisions. For particles of velocity v, it is given by tau is equal to lambda m over v, and the mean frequency of collisions is tau minus 1 equal to v over lambda m, which can be written as NN sigma v. If we now average over particles of all velocities v in a Maxwellian distribution, we have the collision frequency v, which is equal to NN sigma v. Next we will study the diffusion parameters. The fluid equation of motion including collisions is given by mn dv over dt, which is equal to mn partial v over partial t plus v dot del into v, which is equal to plus minus en electric field vector E minus del p minus mn v vector, where again the plus minus sign indicates the sign of the charges. The averaging process used to compute V is such as to make equation correct, we need to be concerned with the details of this computation. The quantity V, however, be assumed to be a constant in order for equation to be useful. Here we consider a steady state in which partial V over partial T is equal to 0. If V is sufficiently small, a fluid element will not move into regions of different electric field and del P in a collision time, and the convective derivative dV over dt will also vanish. We set the left hand side of the above equation equal to 0, then we have V is equal to plus minus E over mv electric field E minus kT over mv delta n over n. The coefficients above are called the mobility and the diffusion coefficient, which are given as mu is equal to q mod over mv is the mobility and d is equal to kT over mv is the diffusion coefficient. These coefficients will be different for each species. D is usually measured in meter square per second. The transport coefficient mu and d are connected by the Einstein relation, which is written as mu is equal to q mod d over kT. The flux of the jth species can be written as gamma is equal to nvj, which is equal to plus minus mu j n capital E minus dj del n. अगर हमारे पास मोबिलिटी ज़ीरो हो तो फिर हम अबव इक्वेशन को चेंज कर सकते हैं इनटू फिक्स लॉ, which is mathematically can be written as gamma is equal to minus dj delta n. This equation merely expresses the fact that diffusion is a random walk process. फिक्स लॉ बेसिकली हमें बताता है कि डिफ्यूजन जो है वो एक रैंडम वाक प्रोसेस है जिसमें नेट फ्लक्स की डायरेक्शन जो है वो डेंस रीजन टू मोर डेंस रीजन टू लेस डेंस रीजन होती है, बिकॉज मोर पार्टिकल्स स्टार्ट इन द डेंस रीजन. This flux is obviously proportional to the gradient of the density. In plasmas, Fick's law is not necessarily obeyed because of the possibility of organized motions, plasma waves. A plasma may spread out in a manner which is not truly random. Our next topic is the decay of a plasma by diffusion. अब हम देखेंगे कि how a plasma created in a container decays by diffusion to the walls. Once ions और electrons wall तक जब पहुंच जाते हैं तो they will recombine. The density near the wall therefore is essentially zero. First we study the case about M bipolar diffusion. M bipolar diffusion is diffusion of positive and negative species with opposite electrical charge due to their interaction via an electric field. अगर हमारे पास आयोनिक क्रिस्टल्स हों तो the fluxes of the diffusing species are coupled, जबकि in a plasma the various species diffuse at the same rate. The fluid equation of motion and continuity equation gives the plasma behavior, but अगर decay slow हो तो फिर हमें सिर्फ टाइम डेरिवेटिव को रिटेन करना पड़ता है इन कंटिन्यूटी इक्वेशन. द टाइम डेरिवेटिव इन द इक्वेशन ऑफ मोशन will be negligible if the collision frequency v is very large. Then we will have partial n over partial t plus del dot nvj is equal to partial n over partial t plus del dot gamma j is equal to 0. It is clear that if gamma I and gamma E were not equal, तो फिर हमारे पास जल्द ही चार्ज इम्बैलेंस प्रोड्यूस हो जाएगा, जिसकी वजह से इलेक्ट्रिक फील्ड सेटअप होगी जो कि इस इम्बैलेंस को रोकने की कोशिश करेगी. The electric field E can be found from here by setting gamma I is equal to gamma I, which is equal to gamma. Using this we can find the electric field vector. Then the equation for the flux will be gamma is equal to mu I n electric field E minus di del n, which is equal to minus mu E n E minus de delta n. The flux of ions and flux of electrons will be equal, and if this is the case, then from here we can write the equation for the electric field vector, which is equal to di minus de over mu I plus mu E delta n over n. The common flux gamma is then given by gamma is equal to minus mu E di plus mu I de over mu I plus mu E delta n, which is equivalent to minus d alpha delta n. As we know that partial n over partial t is equal to d alpha delta square n, and d alpha is equal to mu E di plus mu I de over mu I plus mu E. This is the Fick's law with a new diffusion coefficient d alpha called the M bipolar diffusion coefficient. If this is constant, then the equation becomes very simpler, which is given as partial n over partial t is equal to d alpha delta square n. To find the magnitude of d alpha, हम mu e को लिख सकते हैं very greater than mu I. Then the equation will become simpler, because we know that V is proportional to the thermal velocity, which is proportional to m to power minus 1 over 2, and mobility mu is proportional to m to power minus 1 over 2. Then we get d alpha is equal to di plus mu I over mu E de, which can be written as di plus te over ti di. For te is equal to ti, d alpha is equal to 2 di. The effect of the M bipolar electric field is to enhance the diffusion of ions by a factor of 2, but the diffusion rate of the two species together is primarily controlled by the slower species. इस कैलकुलेशन से हमें पता चला है कि जो एम बाईपोलर इलेक्ट्रिक फील्ड का इफ़ेक्ट होता है वो बेसिकली आइंस के डिफ्यूजन को इंक्रीज़ कर देता है बाय अ फैक्टर ऑफ 2, लेकिन डिफ्यूजन रेट जो 2 स्पीशीज़ का है उसको कंट्रोल किया जाता है बाय द स्लोअर स्पीशीज़। नेक्स्ट हम स्टडी करेंगे डिफ्यूजन इन अ स्लैब। The diffusion equation can easily be solved by the method of separation of variables. For that we let n of rt is equal to t of t, s of r. We make two variables t and s. S is a function of r while t is a function of time t. Then we solve the equation partial n over partial t is equal to d alpha del square n. Since we have two variables, then we get s of r dt over dt, which is can be written as d alpha t of t del square s of r. Similarly, 1 over t of t dt over dt is equal to d alpha over s of r del square s of r. Since the left side is a function of time alone and the right side is a function of space alone, these two sides must be equal to the same constant. Here we call this minus 1 over tau. The function t then obeys the equation dt over dt is equal to minus t over tau, with the solution t is equal to t naught e to power minus t over tau. The spatial part s obeys the equation del square s is equal to minus 1 over d tau capital S. स्लैब ज्योमेट्री में हमारे पास डी स्क्वेयर एस ओवर डी एक्स स्क्वेयर इक्वल होता है माइनस 1 ओवर डी टा एस के, जिसका सलूशन हमारे पास होता है एस इज इक्वल टू ए कोस एक्स ओवर डी अल्फा टा टू पावर 1 ओवर 2 प्लस बी साइन एक्स ओवर डी टा टू पावर 1 ओवर 2. Here we expect that the density should be near to 0 at the walls and to have one or more peaks in between them. The simplest solution is that with a single maximum by symmetry we can neglect or reject the odd terms in above equation. By using the boundary conditions s is equal to 0 at x is equal to plus minus L, then we have L over d tar to power 1 over 2 equal to pi by 2, or tau is equal to 2L over pi to power 2 d alpha. Combining all the above equations, we can write n is equal to n naught exponential to power minus t over tau cos of pi x over 2L. Density of a plasma at various times as it decays by diffusion to the walls is shown in the diagram. The equation n is equal to n naught exponential to power minus t over tau cos pi x over 2L is called the lowest diffusion mode. The density distribution is a cosine and the peak density decays exponentially with time. The time constant tau increases with L and varies inversely with value of d In general, the decay time constant for the Lth mode is given by tau L is equal to capital L over small l plus 1 over 2 into pi to power 2 1 over d alpha. Decay of an initially non-uniform plasma showing the rapid disappearance of the higher order diffusion modes is shown in diagram. The fine-grained structure of the density distribution corresponding to the large L numbers decays faster with a smaller time constant tau L. The plasma decay is shown in diagram. First, the fine structure will be washed out by diffusion. Then the lowest diffusion mode, the simple cosine distribution, will be reached. Finally, the peak density continues to decay while the plasma density profile retains the same shape. Next, we study the diffusion in a cylinder. अब हम डिफ्यूजन को स्टडी करेंगे इन अ सिलेंडर. For this we take the spatial part of the diffusion equation which we used previously. In cylindrical geometry it is written as d square s over d r square plus 1 over r ds over dr plus 1 over d alpha tau s is equal to 0. Here we have one addition term which is the middle one, where s is equal to j naught r over d tau to power 1 over 2. This term merely accounts for the change in coordinates. The need for the extra term is shown in the diagram. For example, अगर हमारे पास कोई प्लाज्मा का स्लाइस हो and in A is moved toward larger x without being allowed to expand, then the density would remain constant. On the other hand, if a shell of plasma in B is moved toward larger r with the shell thickness kept constant, the density would necessarily be decreased as 1 over r. This function is called a Bessel function of order 0, which is shown here in diagram. For this we have two boundary conditions, n is equal to 0 and r is equal to 0. Applying these conditions we get the decay time constant tau. The plasma again decays exponentially since the temporal part of the diffusion equation is unchanged. Higher diffusion modes with more than one maximum in the cylinder will be given in terms of Bessel functions of higher orders in direct analogy to the case of slab geometry. We now summarize our fourth lecture. Summary of fourth lecture is: first we studied the electromagnetic waves parallel to B naught. We found the dispersion relation of such waves propagating parallel to B naught. That was our last topic of chapter 1. Then we started our chapter 2 with chapter 2 about the diffusion and resistivity. We started this chapter with the diffusion and mobility in weakly ionized gases. We studied the Killian parameters and diffusion parameters and wrote their expressions. Next we studied the decay of plasma by diffusion, how plasma decays in a diffusion process. To study these, we also studied the M bipolar diffusion, diffusion in a slab, and diffusion in a cylinder. We calculated mathematically expressions for the diffusion process. That's the end of our fourth lecture.